very common and natural and actually useful to represent the real numbers, not just as a big collection or a bag that we dump out on the floor, but actually along the line. And so here we have a one-dimensional representation of the real numbers, and the power of a number line is that it allows us to contrast two real numbers in comparison. So for example, looking at a number line, if I say something like A is less than B, what that means on the number line is that A is simply to the left of where B is, or B is to the right of A. And so if I say A is less than or equal to B, that means not only A could either be to the left of B, or it could be B itself. A and B could be the same. And similarly, B could either be to the right of A or B equals A. Now also what we could do is we could represent on a number line something like this. If I wanted to talk about the set of all numbers from here to here, this goes from -2 to 3. I could write this as an inequality system, just like we learned about. I could say then that means I know that all my numbers here are going to be bigger than -2 because all the numbers in this set are to the right of -2 on the number line, but also they're left to 3. So they're caught now in between -2 and 3. And so we wrote the set of real numbers according to the number line as what we call an interval. And so there are different ways to represent intervals. I'll show you two quick ways. The first one is by using set builder notation. And so with set builder, I use the same inequality system here, and I set braces, and I'm going to write, this is the set X such that the things in this set have this property. They're between -2 and 3. And again, this means the elements of this set look like this. They look like X, such that X obeys this property. They're between -2 and 3. The other way to represent this interval is through interval notation. And so with interval notation, I'm going to take my starting point along this part of the real line that I'm looking at, so it's -2, and the end point, which is 3. And then all I have to do is just include them in parentheses or brackets, depending on whether -2 and 3 are included. Now the way I drew this is, notice I have open circles here. On my inequalities, they're strictly less than, there's no greater than. So because of that, I'm going to use parentheses. What this means is that anything larger than -2, but really, even if it's really close, so like -1.999 is included in here, and anything going up to 3, like 2.99999, for example, is in here, but -2 and 3 themselves are not included. And that's because we said strictly greater than -2 and strictly less than 3. Now I'm going to show you some examples that show you the variations of intervals that you can deal with, and hopefully it'll make sense. Now I have these 4 intervals here, and I want to show the solution of these in interval and set builder notation, the sets that I'm talking about. So for the first one, I can see that I'm starting with -2 and ending with 9. So in my interval here, I just have to write -2 and 9, and I just got to figure out how to cap it off. Well, I see that the circle's included on the -2. That means that -2 is included in my answer, but +9 is not. So everything up till 9. So that's my interval and interval notation. In set builder notation, I just use my squiggly brackets or my braces, and I say this looks like everything, all the x's, such that x is less than or equal to, x is greater than or equal to 2 and less than 9. And so there's my answer in set builder notation. Okay, for the second one, notice that I have a 1 and a 5. And this time they are both bracketed, right? Because the 1 and the 5 are included. So in set builder notation, I do my braces. So this looks like all the x's where I have that my x has to be bigger than or equal to 1 and less than or equal to 5, like that. Okay, for my third one here, notice I have an 8, but there's nothing on the left-hand side. So you can imagine there's kind of no endpoint going to the left direction. So the way we handle that is I say there's negative infinity up to 8, and I always put a parenthesis on infinity because you can never obtain infinity. And I get a hard bracket on my 8. In set builder notation, I do my squiggly brackets. This looks like all the x's, where the only condition I have to meet then is x is less than or equal to 8. Because you can imagine, I can never be, I'm always greater than infinity, so we don't even need to, we're always greater than negative infinity, so I don't even need to write that out. And the last one here, we can see that I'm starting with 17, and I go on forever, so we know that's going to be infinity. And the 17 is not included, so to parenthesis, and in parenthesis goes on the infinity as well. In set builder notation, I have my x's, and all I need to make sure is that x is greater than 17. As long as I'm greater than 17, I'm in this set. I hope these make sense. Interval notation, set builder notation are very useful, and it's important to be able to jump also from the intervals to the line, the number line. So if I start with this, it's important to be able to get back to this concept and just be able to visualize where in the real numbers I'm talking about. If you have any questions, please let me know. I'd be glad to help, and thanks for listening.